Thank you, sir. Thank you for the opportunity. I'll start in a minute. I hope my screen is visible to all of you.
Yes, sir.
Am I audible? Am I audible?
Yes, sir. Yes.
Okay. I'm planning to use some smart board or that graphical tablet. So I'm using this journal. Okay. So thanks once again, Dr. Rita Pure sir, and the organizers of this beautiful FDP on artificial intelligence and machine learning in mechanical systems. The title of my topic is, though sir was talking that few faculty members will be taking fundamentals followed by applied. So I have combined here both fundamentals and applied, and also what are the trends going on in the industry in the space of artificial intelligence. Okay, so accordingly, so this is a mix of a few mathematics, then theory, robotics. So it will be a sort of a journey. It is a sort of mid journey. It is theoretical based. It is some robotics fundamentals are required. Then I will be talking about different models, and also I will try to touch on what exactly is happening in the space of robotics. Okay, so accordingly, the title of my presentation here is Physical Intelligence Using Lay Robot, and I will be focusing on learning, control, embodied AI for real world robots. Again, the motivation why I have taken this topic, because all of you, even when I was giving my address, most of the address I have generated from generated using Chat GPT. Okay, and I can show over here. Okay, so this address I have generated using Chat GPT. Okay, and I hope that, see, when we are saying that we should learn fundamentals of machine learning and AI, but now the Chat GPT and all those large language models, they have reached to such a level that we should be really very fast to adopt the AI technology for mechanical engineering, because people are talking about embodied AI or physical intelligence, and that is the next challenge. Because today only I have heard the news from Google that, so previously when Google was developing the code, today there is the news that the work, the coding work which was taking 1 year, now that work can be completed within only 1 hour. So such is the pace of large language models or AI, and now we have to keep pace with that. And being a mechanical engineer, this is challenging also, and lot of opportunities are there. And accordingly, since opportunities are there in physical intelligence or embodied AI, and which is not possible for computer engineers, by the way, and I'm a hardcore mechanical engineer. I have good interest in AI and ML, but basically I'm a mechanical engineer, and always advocate or always support whatever is going as far as mechanical engineering field is concerned, because that is our bread and butter. Okay? So opportunity challenges are there. AI is facing a lot of challenges, and we as a teachers, we are facing those challenges also. Today only, when I was doing a lecture on statistics and probability for data science, I asked this question to my students. I asked them whether I am relevant. Most of the people, most of the students, they kept mum. They are not talking anything about. They are not answering my question. Statistics, stat and probability for data science. But we are very fortunate. We as a mechanical engineers are very fortunate. Whatever happened to AI, will remain relevant, because our basis, that is
Sir,
thermodynamics.
sir, sorry to disturb. Your screen is not visible.
Okay, okay. So we'll remain. नाही का आता आता दिसतंय का? My screen is visible to all of you.
नहीं नहीं दिसत.
Okay,
परत 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 शेअर करताय.
okay. It is visible.
हा
Yes.
प्रेझेंटेशन मोडला टाकताय.
Actually, I need to write over here. So I'm
Okay,
keeping
okay,
this.
okay, okay, sir. Yes, sir. Okay, please continue.
Okay. So I was talking about the relevancy of mechanical engineers in the age of AI. So if you, and I ask a question, or this question can be posed to audience also. If I ask you, what is temperature? What is the basic definition of temperature? So temperature is what? Temperature is average measure of kinetic energy of all the molecules. For example, in 1 meter cube of space, of the order of 10 raised to 26 molecules are there, and it is not possible to count each and the kinetic energy of each and every molecule. So what we do? We average it out. So our temperature itself is statistical. The temperature distribution follows Boltzmann distribution. So probability is there. So my point here is that, see, the initiation of AI, whatever you talk about AI or ML, they cannot go beyond mechanical engineering. It's very difficult to, it is very, very difficult to avoid this challenge of mechanical engineering, which is basically uh, because of entropy. So with this, I would like to provide you here what is the motivation of having this topic. So we know that robots must act in the physical world, not just perceive. See, so there are two things in robotics. Traditional robotics or classical robotics is there, and here I will be talking about physical AI or embodied AI, where data, then robotics fundamentals, control fundamentals, kinematics, everything is combined together. Even vision models are there, large language models are there, sound models are, audio models are there. Everything is coming together and they are making a model. The model is called as physical model, or, and right now people are talking about those models also. Currently, if you search on the internet, so for 3 to 4 years back, ChatGPT came. I think 2 years back, ChatGPT came, and everybody was talking about large language models. And currently, at this point of time, a lot of investment is happening in world models, and world models are nothing but the world models are nothing but taking everything into account. For example, physical systems, their language, vision, audio, then your surrounding, the whole thing taken into account, and that things combined together, and that those things become very, very smart and then become intelligent. Okay, so this is the motivation. So physical intelligence is about that. So the motivation is, so here, see, I know that most of you may have worked in classical robotics arena, or you may be working, or you may be having slight knowledge of artificial intelligence and ML. Okay, and I'm taking this as a cue. I'm talking about what is currently happening and how we can leverage whatever is currently happening and immediately start our research, because we don't have, really speaking, we don't have time to really start from the fundamentals. Okay, because everything is available on internet, everything is available on large language models. We can immediately start our journey. So this is my motivation and this is my objective. Okay, so the robot must act in physical world, not just perceive. So this physical interaction involves uncertainty, contact, and dynamics. Now, data-driven learning enables adaptability beyond hand design control. For example, if you take industrial robot, if you take example of manipulators used in industry, those are, their controls are hand designed. The controls are embedded onto the microcontroller, and if some different environment is, if that industrial robot or manipulator is kept in different environment, that manipulator will miserably fail. It cannot be generalized. Physical embodiment tightly couples perception and action. Okay, so this is very important. Perception, that is sensing, and action. Action means the commands which we send to the robot. Those, then making errors and delays in sensing directly affect control outcomes. For example, see, you can imagine. So we as a human being, we are a general purpose sort of thing. So we are trained for walking. For example, a kid start learning walking. A kid start looking at the thing. A kid start understanding the surrounding. And if he asks a kid, please bring that apple to me, then what happens? That kid go, that kid pick up the apple and bring us to us. Okay, So this is just the instruction given to the kid. Later on, after training the kid for that, if we ask our kid, please bring that ball to me. So the kid will just look at the ball, the kid will go there and it will bring the ball to you, ball to us. So this sort of training or this sort of learning or this sort of intelligence is called as general intelligence, or actually not. When I'm talking about here, we are actually everything is artificial intelligence, but this artificial intelligence is generalized, it is not specific. General purpose behavior requires learning from diverse real world experiences rather than task specific and brittle controllers. For example, I have given example of manipulators using industries for particularly industrial robotics. In those manipulators, the controllers are task specific. We cannot put those manipulators for different application. If you want to put those manipulators for different application, we have to throw away the current controller and from scratch we have to design the controller. And not only that, all this objective of this physical intelligence, the robot should learn in the way a child learns walking. And when I'm saying walking, it involves everything. So when child is walking, or we for that matter, if we walk, we have sense of everything. Our motion is physical, but we look at the things, so that is vision. We listen to the things, that is audio or that is sound. Then we touch to the ground, that is contact. Then ground may be even or uneven, so there is uncertainty in the environment. Then if possibly something happens, some loud noise comes, and then we hesitate, then we tend to fall. So this is a sort of error given by the environment. Now imagine that we as a human being, we can adapt to the surrounding, and depending upon natural intelligence or general intelligence, we take the decision and move from one position to another position by taking cue of the surrounding. And from where we are taking the cue? From our sense organs, eyes, ears, nose, then our legs, hands. We take help of everything, then we take decision, and then we move and do our task. So people are talking about, or this artificial intelligence community, they are talking about this level of intelligence. And this is really, believe me, this is very really challenging, because see, development of large language models like ChatGPT or DeepSeek, for that matter, any model. So this is just a manipulation of language. But here in robotics, physical motion is involved. And when physical motion is involved, then Newton's second law of motion is there, then different uncertainties are there, errors are there. Okay, so everything has to be taken into account, and then we can decide about that intelligence. And that intelligence is called as physical intelligence, or it is called as embodied AI. And if you go further, so everything will then be packaged as a world model. Okay, so what is world model? Where currently a lot of investment is happening is embodied AI plus all these large language models, vision models, audio models, everything. We just pack everything together and give it to the customer. So that is world model. Okay, so with this motivation, I will start my further presentation. So what is physical intelligence? The physical intelligence is also called as embodied AI. Okay, so this is a classic definition of physical intelligence. Physical intelligence is the capacity of an embodied agent. So here agent means a robot. For example, our browser to which we are typing prompts, that can be a sort of agent, along with API, which is interacting with large language model. Okay, so here this embodied agent means embodied agent, a robot. So here embodied agent means robot. So physical intelligence is the capacity of an, you can think here, a leg robot for that matter. Okay, so physical intelligence is the capacity of an leg robot to learn and execute goal directed policies through closed loop interaction with dynamic physical environment, respecting the constraints imposed by physics, sensing, and actuation. So many things are happening over here. So many things are happening. So here we can think, so this is a sort of leg robot. We can think that this is a leg robot. So this is about robot. And what is happening? So goal directed policies. So if you are from robotics, these policies are nothing but you take the observation, and by taking the observation, you give commands to the actuators. Okay, our policy is nothing but a function which is indicated by pi, which take observation, and these observations are mapped to the action. And here when I'm saying action, those who are from those, some of you may be from a reinforcement learning background, they can understand it. So these actions are mapped to joint commands, and we give joint commands for movement of the robot. So try to understand that. So what is policy? And policies are goal directed. For example, if you want to go from one position to another position, that goal has to be reached. If the goal is not reached, then our robot has failed. So that should not happen. What is policy? Policy is a function which take observation or joint states and map to the action. What are actions? Actions are the joint commands given to the actuators. Okay, and it's a closed loop between joint commands and the observation. So this interaction is not static interaction. This interaction is dynamic interaction in physical environment, and this physical environment is not inert. Laws of physics are satisfied. If you talk about robot, Lagrange equation is there. Lagrange equation can be reformed into Newton's second law of motion or momentum equation. Then constraints are there. Then sensing is happening with the help of sensors, and then finally actuation is there by virtue of the motors. So everything is coming together. So this is physical intelligence. Then what is physical intelligence? It is an ability to perceive, decide, and act in real world. Now here I'll be talking about everything applicable to real robotics, not just sort of simulation. Because if you think about physical intelligence or application of artificial intelligence in robotics, so many software frameworks or so many simulation frameworks are available. We can train a policy and we can simulate the policy on the simulation framework. For example, simulation frameworks like ROS is there, then Mujoko is there, PyBullet is there, or for that matter, many physics engines are there. Some of you may have worked on Gazebo. All these physics engines are there. We can train a policy by developing a code on by using PyTorch or any other AI framework, and you can run the simulation. But that is not the point. Our aim is here. Aim is to run the policy on real robot and in shortest possible time. Again, what is physical intelligence? It is grounded in physics. Forces are there, geometry is there, and dynamics is there. We cannot forget physics. See, in large language models, we are using ChatGPT. Then we are using DeepSeek. Even for that matter, we are doing vibe coding. Say, while developing vibe codes or while getting some output from ChatGPT, we don't have to bother about physics. Okay, but here when physical AI is there and when robots are there, we cannot forget physics. We cannot forget, at least when we are talking about classically, we cannot forget Newton's second law of motion or this momentum equation. Okay, so physical intelligence is grounded in physics. Forces, geometry, and dynamics. Constraints are thrown by geometry. Then dynamics. When dynamics is there, then dynamics is error prone. And it must be this physical intelligence must be combined with perception, or that is sensing. Then control is there, and then perception, control, this physics, they are coming together. And here we are talking about learning. It is not that there is some mathematical model of a robot and environment is available and we are designing a controller by doing some sort of classical way of writing a code and flashing onto the microcontroller. It is not like that. Our controller or our policy is learned by providing a lot of data. Okay, so paradigm shift is there. So it is not a classical control based robotics where world model is available, state space equations are available. Then you have all these coefficients you can choose. Like you can use any control algorithm. You can put that control algorithm like model predictive control you can choose, and then you can hard code the control and you can run your robot. So this here I'm not talking about that. Here I'm talking about lot of data is available. Data is coming from vision. Data is coming from language. Everything is combined, and now your robot is learning to walk. Your robot is learning to dance. Okay, so this sort of thing we are trying to do. Okay, so this is about physical intelligence. Now to understand how we can go from, again, I will be interchangeably using embodied AI and physical intelligence. Okay, so physical intelligence is embodied AI. Some people can call, Google can call this as embodied AI. Some other company can call it as a physical intelligence. It doesn't matter. Nomenclature doesn't matter. Okay, now here, so how we can go, how, now here both are combined from classical control to embodied AI. How this journey is happening. And this is our regular control uh, schematic. So this is robot plus environment. Okay, and in robot plus environment, now this is the mathematical equation. This is our state space equation. X dot. So this is generally state space equations, or equations are first order equations, where x dot is, again here we can talk, x dot is rate of change of displacement, that is velocity, which is function of this. Again here x is position, u is the control, and w is some sort of disturbance. So x dot is a function of state, that is position. For robots it is position, then control, and some error is always there, some noise is always there. Okay, so this equation is available. Classically this equation is available. Okay, now what the sensors are doing, the sensors senses the displacement, or senses or perceives the positions. In our case, in robots, sensors senses the positions. Okay, and now see, this is indirect. Y of t is function of h of x, that is position, and some, again, sensors also have some noise. So this y of t is going to our controller. Okay, na? So this is controller, and in this controller, what this controller is taking, pi later you use for policy. Again, I can use this controller and policy interchangeably. Controller and policy are one and the same. So what this controller is doing, controller is taking y, that is signal from the sensor, from 0 to t time step, and it is throwing, or it is giving output as u of t, or the control signal. This control signal goes to actuators. In our case, in robotics, this actuator is nothing but, it can be hydraulic motor or it can be electric motor. Okay, and this control actuator is going, and it will control. It will go over here, and now this is the dynamics, and according to this dynamics, further we'll get x of t and y of t. So here in this case, this plant is nothing but robots plus physics. We cannot forget the physics. For x dot t is this function, state space equation. Sensor don't give us full observability. We don't know most of the things. Sensors are giving only partial observability. For example, if a manipulator is there, we know, suppose a manipulator has 6 motors, then we know only about 6 positions and 6 velocities, or max we can know the acceleration also, but we don't know much about the environment, what is happening at the surrounding. Then what happens? So this sensor is offering, now here y of t is equal to h of x of t plus v of t. So it is giving partial observability. On the basis of this partial observability, we design our controller, or we design our policy. What is this policy? This policy is function of y, where y is the sensor signal sensed by the sensor, and we get this control signal. In traditional robotics, what we do generally, this model is available. when I'm saying model x dot equal to f of x u w. So this model is available. This model is available. Then we know we know the mathematical function of the sensor. So we get y. So this block and this block, they are available. On the basis of that, we design either model predictor control, or normally we can design a PID controller or PD controller. Okay, and this PD controller will drive the actuator, or this u of t signal will drive the actuator, and the things will move, or the robot will move. So this is traditional way. But in embodied intelligence or physical intelligence, everything has to be taken into account. We cannot design controller, or we cannot design policy in isolation with this. And generally in real robotics or in complex environment, the model is not available. When model means what? This x dot is equal to f of this f of x u w is not available. Similarly, we don't know what is happening at the sensor. Most of the time, the things are stochastic. So the things are random. Errors can be generated. So what is this embodied intelligence is doing? Embodied intelligence is working in the loop. It is taking everything into account, and it will give you a policy. So ultimately what we want a controller or a policy which will output control signal. This control signal will run the motor, electric motor or hydraulic motor, and by running the hydraulic motor, our robot will move in the environment. Okay, so this is the objective. And now we have to achieve this object not by hard coding, not by hard coding the controller, by using the data. So everything is based on data. We'll develop our controller by generating the data, by training our controller, and the data is multimodal data. It is not only that some positions, velocities are given. We can take vision data, we can take audio data, and for that matter, we can take also language data. So everything is taken together. Data can be taken, and then we can learn the policy, or we can learn the controller. So this is a journey from classical control to embodied AI. I hope that you people are listening to me carefully. Again, the question can be asked, why learning-based robotics should be there? Because see, if you look at the classical robotics, most of the things are settled. See, the humanoid robots were learning 10 years back also. Or manipulators are there in industry for so many years. We are using ABB robots. Then even quadrupedal robots are there. And then why people are talking about learning-based robotics? So let us discuss about that. Model-based control. And when I'm saying model-based control, PID is also model-based control. Okay, model-based control assumes known dynamics. Known dynamics is what? So this first order differential equation is available. And in this first order differential equation, so this model is available. So in classical control relies on accurate analytical model. If the model is not accurate, then this U will be wrong. And when this U will be wrong, our robot will fall, our robot will fail. So in real robots, if F is unknown, okay, so this F is unknown, time varying. So F can be function of time, and discontinuous due to contact, friction, and wear. Believe me, so we can think that this function can be linear function, but because of discontinuities, because of contact, friction, and wear, this function can be a nonlinear function, and it is time varying. So look at the complexity. Okay, so because of this complexity, this learning-based robotics is there. System identification does not scale to contact-rich tasks. Identification works well for smooth dynamics. So this is linear quadratic regression. Then model predictive control. Okay, so all these models or all these controllers are based on smooth dynamics. But when we are walking, like human being, we as a human being, when we are walking, what is walking? After all, walking is walking is a control fall. And when we are trying to fall in a control, then we are impacting on the ground. When we are impacting the ground, depending upon the ground condition, sleeping is there. Depending upon the down conditions, sticking is there. So where dynamics is hybrid, dynamics is complex. We no longer we can avoid, or no longer we can neglect the non-linearities, or contact has to be taken into account. So this is another reason why one should go for learning based robotics, and this is very successful. Then learning replaces explicit modeling with policy optimization. Okay, so instead of wasting, I'm not saying here wasting, instead of putting a lot of effort to trying to understand the exact model of the system, the how we can take into account contacts and all the non-lities into account, why not to directly attack the policy? And when I'm saying policy, why cannot we directly get this using the data? Okay, so if you are in the situation to get this directly on the basis of data, the whole of this headache is taken implicitly implicitly into account in this one expression. Okay, so instead of identifying model, learning directly optimizes the controller. This pi of theta is, and when this theta means parameterization. So theta, these are nothing but the weights of a neural network. So here indirectly pi of theta, it says that this is not a general mathematical expression, it is a deep neural network. So we can train a deep neural network where we'll try to find out by optimizing or by minimizing or by formatting some objective function, we'll find out theta. And in this pi of theta, if we put the observation from 0 to t, then we can get u of t, and then the control signal, and then this control signal will drive the robot. Okay, then robustness comes from data, not margin. Classical robustness relies on worst case bounds. Learning based methods achieve robustness by training across diverse disturbances, geometries, and conditions, implicitly covering uncertainty. Okay, so what we do in our regular robotics, regular or classical robotics, we put bounds. Okay, something will not happen. But here in learning based methods or learning based paradigm, everything is taken into account implicitly. If you have diverse set of data set, which is taking into account disturbances, geometries, and uncertainties. And finally, generalization is representation driven. Hand design controllers are task specific, as I have given example of industrial robots, that is manipulators used. But here learned representation captured share structure, enabling transfer across tasks without rederiving controllers. So we don't have to rederive. For example, now see, from ages, I am 50 years old. For last 50 years, I am walking. Okay, and now, or for that purpose, a small kid of 2 years old, he easily walks without much retraining. Once he start walking, then once he start walking on plain ground, if some disturbances are there or even ground is there, that the kid will not fall, because that kid will adjust his position. It will learn implicitly. So that is learning based robotics. But what are the challenges? So I will go slightly faster. Severe sample efficiency in the physical world. Then safety constraints during exploration and learning. Then sim to real gap due to unmodeled physics. Strict real-time latency requirements, partial observability, and sensing uncertainty. Okay, so I will share these slides with you later on. Please go through it, because I want to completely take Lee-Robot framework. It is a really very beautiful framework, which I wanted to very seriously take it over here. Okay, so I'll just go fast. Now, introduction to Lee-Robot. So this physical intelligence, right now, see, when you are sitting over here, you are listening to my lecture. Right now also, you can install this Lee-Robot on your computer and you can start coding. And you can take help of ChatGPT or DeepSeek. Then you are in the business. So that is my motivation. Instead of teaching you how this neural network is working, how this objective function can be formulated, how we can backpropagate it. So all these things you can do of your own. My objective here is that, oh, after 1 hour, after finishing of this lecture, you should start working. And particularly, this is useful for the researchers who are searching for new problems. And this is, believe me, this is current. World models are coming. And when world models are coming, will become very important. Mechanical engineers become very critical. Okay. So what is this Lee robot? So I will first I will just go through this slide and then I will show you this Lee robot framework. This Lee robot is open source robotics learning framework developed by Hugging Face. And all of us must know this is a time for mechanical engineers or everybody of us to work along with or side by side of Hugging Face. So Hugging Face, all models, you just take name of a large language model, any model, any vision model, any sound model, you just name it. All the models are there on Hugging Face. So this Lee robot framework, it's very much, we can think this Lee robot framework as a operating system of robots, operating system of physical AI. Like some of you might have worked on, might have worked in robotics using robot operating system, ROS1 or ROS2. You can think Lee robot as a sort of robot operating system for physical AI. And not only, this is not just a simulation framework. So believe me, this is not a simulation framework. It focuses on real robot data sets and policies. So data sets, standard data sets are available and policies are also available. So you can directly train your real robot. You can take the policy from Hugging Face, from Lee robot. You can fine tune the policy and you can run your own robot. Standard interfaces for standard robots are also available. I'm going to discuss it. So this is designed for reproducibility and scaling. So reproducibility is very important. For example, I have developed something. I am developing some simulation. I have done this policy evaluation my own real robot. But if I'm not able to reproduce it on any general robot, then it is useless. But this problem is addressed by Lee robot. And scaling is also important. So scaling is also there. Then the approach is data-centric robotics. I'm going to discuss this in great detail. And this is very simple composable abstractions, close integration with model ML stack. And what is the most important or most widely available and widely used ML stack? You can think about scikit-learn is there. It can be combined with scikit. It can be combined with PyTorch. You can use TensorFlow for that purpose. So you can take the help of all the ML stacks. You don't have to invent the you don't have to reinvent the wheel. And learning curve is also very smooth. See, if you decide, you can learn Lee robot within 2 or 3 days, provided that you have some basic understanding of robotics. Okay. So here, there is no question of reinventing anything. Everything is available. You have to just start your journey in physical AI. Okay. And if my screen is available, if my screen is visible, I will just bring you to this. Okay. So everything is there. So you just go through it. My role here is to just facilitate whatever is given here and just try to bring some fundamentals into the discussion. Otherwise, everything is very, very doable. It's very simple. Okay. So when you are listening to my lecture, please go through this Hugging Face, because this is the first step. And if you don't start this step, that means intentionally we are keeping us back, because this thing is currently happening. Okay. So I hope that you people have visited this website on Hugging Face. Okay. So what is this Lee robot ecosystem? So you can think that this Lee robot ecosystem similar to robot operating system. Like ROS is there, ROS1 and ROS2 is there. Everything, literally everything is there. So what it consists of? This Lee robot ecosystem and support. It consists of robot hardware interfaces are provided. That's the beauty of a Lee robot. So hardware interfaces are provided means what? They have given few standard robots. For example, I will bring your attention to this. I'm going to discuss those things, those robots and all those things. So you can just see over here. So these standard robot hardware interfaces are there. That is SO101. So this is a manipulator. And you people may be knowing that Unitary is a humanoid robot developed by Unitary. Okay, so believe me, so this is a great thing. A humanoid robot can be trained with Lee robot using the data which we are going to discuss, and this is a huge thing. So all these hardware interfaces are available. You can develop your own code, you can develop your own, you can 3D print your own robot, and you can pick up architecture very much similar to SO101. And by the way, this SO101 is 3D printable. All the CAD files are available, all the motor specifications are given, and you can just assemble it and you can run your policy, and you can say, okay, I'm in the game. Okay, so this is about the standard dataset formats and loaders are given. So we don't have to redesign our dataset format. See, by the way, we have to train a model, we have to train a policy. And when policy has to be trained, or any machine learning model has to be trained, and of course, data is required. And we cannot provide data in any format. So that standardization, how we can create the data, how we can put data in the standard format, and after putting this data onto the Hugging Face, or after storing our data on our local computer, how we can load the data and train our policy. That is also provided by Lee robot ecosystem. Not only that, standard policy architectures which are going to see, that are also provided by Lee robot. Then training and evaluation pipelines are also given. Low cost manipulators, like I have talked about SO101. Then mobile manipulators, camera equipped arms, extensible to custom robots. And that's the beauty. So you don't have to just depend upon whatever robot hardware interface they have provided. We can 3D print our own robot. We can fix our own camera. We can generate the data set. We can devise our own policy, and we can train our robot. And believe me, it will not take more than, see, the training takes a lot of very less time. Within 2 or 3 hours, our robot can be generalized. Okay, that we are going to see next. See, I was talking about this robot hardware interfaces. Now, see, these are the common. So this is manipulator. Okay, so all these 3D files, 3D printable. So this is 3D printable. All motor specifications are given. Controller, again, when I'm saying controller, policy is higher level control. And this microcontroller, like this flashing of your code on Arduino and all this, this is lower level control. Lower level control details are also provided by Lee robot on for this SO101. Then this Lee KV manipulator. So this is mobile and plus manipulator. And believe me, so many applications we can envisage for this type of robot. And this is not hard coded. We can train our data set, and we can put this type of robot in application having physical intelligence. Okay, then another this thing is, so you people might have seen how Unitary is dancing. Okay, so Unitary humanoid hardware interface is also available, and this is mobile robot. Okay, Earth Rover Mini. So these are the few examples which we can train, which for first thing, for which we can generate the data. By using that data, we can train our policy, and we can run our policy on these robots. So this is a huge thing. We don't have to invent anything. Everything is given to us ready-made. Only thing is that slight integration is required. And after all, integrator role will going to remain. Okay. And that I am doing over here. Now I will talk about, now see, try to understand. Now this robot as a physical machine is available to you. This as a hardware is available to you. This humanoid robot as a hardware is available to you. And now what we have to do? We have to train the policy. What is policy? Policy is nothing but a controller, but that controller is not hard coded, and it requires data. Okay, and now how we can create the data, that I am going to talk about. So there is physical interaction and data generation. So what is, how it is happening? Embodied interaction loop. Robot interact with the real world through a closed sensor actuator feedback loop. Means what? How a child learn walking? A child learn walking by really walking on the ground. See, try to understand. Child is, see, we don't do like that. We don't ask our child to learn walking through language only. Of course, initially we give instruction. आपण काय म्हणतो, बाळा इथून तिकडे जा. Please go from this position to this position. But that child or kid physically goes from one position to another position. Okay. So robot interacts with real world through closed sensor actuator feedback loop. Observations include vision, RGB depth, proprioception, force, torque, actions. Actions are what? Join commands, end effector motions or torques. So this data, whatever data is generated, it consists of everything whatever is discussed over here. So it consists of vision. It consists of force, torque, action commands, then end effector positions, motions, and torques. Demonstration and experience. So teleoperation. Now I'm going to discuss in detail what is this teleoperation. And this teleoperation is possible using VR headset, using Unity and all those type of tools. Then kinesthetic teaching, like cobots are there now. So cobots, we know cobots. We teach the robot by moving from one position to another position by physical motion by physically moving the robot from one position to another position. So this is kinesthetic teaching. Then we can script the controllers. So this is, again, we are going towards this conventional way. We can script the controllers, and this is how we can generate the data. And what is that? What this data consists of? Data consists of each episode records a trajectory consisting of observations and actions. So here, mathematically, the T is what? T is a trajectory. And what is trajectory? The people from robotics, they can understand that when a manipulator, when the end effector of a manipulator is going from one position to another position, so this complete motion as a function of time, as T is going from 1 to T, where observations at time T and actions at time T are recorded. So this is called as a trajectory. So all these trajectories are recorded. And these observations are not only observations of joint positions, velocities, accelerations, torques, contacts. This observation consists of images also. This observation consists of sound also, probably. Okay. And actions are what? Actions are the actual command given to the end effector, actual command given to the electric motor or hydraulic motor for that purpose. So everything is recorded. Okay. So each episode, and here I'm talking about data generation. So while data is generated, each episode records a trajectory consisting of observations and actions. So this is a very important thing. If you understand this, you have understood 25% part of the physical AI. Okay, now we have understood that data set consists of these trajectories. Now, data-centric learning robot. So what happens? Now we have generated the trajectories. Okay, we know how we can record the data in what we want in the data. The next thing is how we can organize the data, because if proper organization of the data is not there, then it is very difficult to train the model. The people who are working in AIML, they can understand that. We do a lot of data cleaning before sending data to the model, even for simple neural network, simple deep neural network, even for simple image recognition problem. Lot of data cleaning is required. If the data is not clean, if you are taking standard data set, then there is no problem. But if you are developing your own application, then a lot of data cleaning is to be done, and data has to be put into structured format. So structured robot data sets are provided by Lee robot. So Lee robot organized data into this time aligned observations. What are those? Actions, episode boundaries, calibration, and metadata. So metadata is information about the data, and generally metadata is given in JSON format, and it emphasizes on reusability and reproducibility. Then learning paradigm consists of what? Imitation learning, behavioral cloning, offline reinforcement learning, and visual language action. So these are the three paradigms generally used in physical AI. And here, when I'm saying policy learning, this policy learning, in a way, you can understand that this policy is nothing but a very deep neural network, or it can be a transformer, or it can be combination of convolutional neural network. Everything is combined, and that becomes a policy whose weights are found out. Okay, so this is a policy. In a simple way, you can understand this policy is nothing but a deep neural network. And what is this theta? Pi. Pi is parameterized with theta, and this is the loss function. Okay, so this is the loss function. This a is whatever a. So a we are getting from the data. Pi of theta is the output of this neural network, and now we are trying to find out theta by minimizing this objective function. And this is the normal way of doing the things. Okay, this is normal way of training the model in ML. I hope you are understanding it. Okay, and this is the expected value. Because why it's expected? Because everything is stochastic. It is not that we are following the same trajectory every time, because the different trajectories will be there. A lot of randomness will be there. Sometimes there will be failure of the manipulator, or failure of the, sometimes expectation is coming over the function which is parameterized with theta. Theta is nothing but, you can think this theta as the weight of the neural network. And what model architectures generally are used? So vision encoders are there. In the vision encoders, convolutional neural networks are there. Vision transformers are there. Those who are who have done some little bit of vision modeling, they can understand these VITs are vision transformers. The architecture of CNN and VIT or vision transformers are slightly difficult. Then temporal models are there. We can even use recurrent neural network transformers, or multimodal sensor fusion is there. Okay, everything. So most of the time things are combined together, they are integrated together to get a robust model. And we'll going to see few architectures, model architectures later on. Okay, so this is about dataset centric learning in Lee robot. After that, what we do? See, here we got the data. What data in mathematically? What this data? Data is trajectory. After this data is taken, this objective function is formulated. This objective function is formulated. In this objective function, A is the action, and action is what? Actions are the joint commands, and which are actual records. Pi of theta is what? Output of the neural network, and we are minimizing it. By minimizing, we are finding out theta. So policy is now think that the policy is available, and now we are going to deploy this policy. So how this real world policy can be executed on the real world? See, in physical AI, emphasis is on real robotics. It is not only simulation. If simulation is there, we can do wonders. But the real challenge is that you have developed a policy, you have trained a policy, and now you have to use that policy on the real robots. So trained policy runs on the robot under real-time constraints. And this is the inference loop. What? You take observation at time step t. Now this is the parameterized policy, which is parameterized with weight theta. You put it there. So this is the function. This function is nothing but a neural network or a transformer. You put this observation here, you get action. And what are those actions? A of t. A of t action is nothing but the joint commands you are sending to the end effector. Joint commands you are sending to the actuators like electric motor or hydraulic motor. So this is happening. And various architectures or various algorithms are there, how you can achieve this. Then not only that, safety and control integration is there, action bounding and filtering, all these things are there. Lower level control ensures stability. Again, so this policy, pi of theta, is higher level policy. Of course, low level controllers are there. For example, if you are giving, if you are asking your actuator to move by say 30 degrees, or for that matter 15 degrees, then ultimately you have to send current to the stepper motor or servo motor. That will be taken care by the low level controller. There will be some sort of motor driver will be there. That motor driver will take command from microcontroller like Raspberry Pi for academic purpose, or STM for that matter. So it will take lower level controllers are there. Here I am not talking anything about lower level controllers. Lower level controllers are the part of execution at your end. Learning arguments not replace controller. See. Then continuous improvement and low. So new rollouts, dataset expanded, policy retrain and fine tune. So this is going on again and again. For example, you have developed a policy using available data set. Then you run that policy on your robot which you have developed. You record that data set and you can fine tune it. And this loop will go on and on, so that a day will come when your robot will become a very fine tuned, very excellent, and it will become really intelligent. And that is the, and everything is integrated. We don't have to look for any other code for that or any other framework for that. Lee robot is sufficient. Okay. The next thing is the real thing. How we can install robot? It's very simple. If you have Windows machine with you, if you have Ubuntu machine with you, right now you can install it. So you create a virtual environment. Then source the environment. And why this virtual environment? Because you don't have to disturb your current installations, Python installation. So have a virtual environment, source it. Then this setup tools are required. So just install it. Then clone this repository. Everything, all the instructions are given. Just for sake of completeness, I am discussing over here, because sometimes you can face some challenges. So clone this repository, cd to layer over, and just give this command. And additional utilities are required if you if you want to simulate it, if you want environment. So gym utility is there. Then numpy required, scipy is required, and for image specific tasks or image specific data set, OpenCV is required. Without OpenCV, it's very difficult to do any sort of image training. Okay. So and along with that, you can install PyTorch, you can install Torque audio, you can install Torch Vision, and even you can install this thing, TensorFlow, TensorBoard. All this thing you can install on a virtual environment, and you can start your journey in physical AI. And I hope that not everybody, but at least 2 or 3 people will try this on their computer. Believe me, because see, people are talking about world models. Amazon has invested a lot of money in world models, and we should do something of this kind. Now I will talk about how this Laravel data set will look like and how we can generate it. So Lee robot dataset, it provides a unified reproducible representation for real robot experience. It enables data set centric robotics. All these things are already discussed. And what is the core structure? Again, this data set, D is for data set. It consists of trajectories going from 1 to n. Okay, so D is for data set. The data set consists of what? Is trajectories. And each trajectory consists of what? Observation, action, where this T is going from 1 to Ti. And what are these observations? What are these observations that is O of T consists of? Observation consists of RGB images. Even it consists of video recordings. It consists of RGB depth images. Then joint positions and velocities. And it's very easy to take joint positions and velocities with the help of sensors. Then optional forces and tactile signals are there. For example, if there is ultrasonic sensor attached to your robot, so it can take the data. So it consists of observations. What are the actions? See, when your robot is moving in a real world, so these joint positions and deltas, which are end effector commands, which we are commanding to the actuator, those are really available from the controller, from low level controller. Even for higher level controllers, we can record that. Okay, so this consists of data. So observation consists of RGB images, joint positions, velocities, then all these tactile sensors and all those things. Then actions are what? These are the real actions. These are the real joint commands which we are sending to the actuator. See, believe me, the ultimate task, how robot can move, how humanoid robot can move. You talk at length. You can talk for days about all these things, but ultimately, how robot move? By virtue of the joint commands. So these are very important. Okay, so data consists of, along with that, this temporal element, like what is the control frequency, how the sensors are synchronized, all these things are there. Now creating our own data set. task and control definition. Clearly specify the robot task. For example, you want a pick and place robot, you want a robot for pushing option, you want a robot for navigation, etc., etc. Okay, we can have a general purpose robot like human robot consists, it can do everything, but initially we can specify the control task, we can specify the robot task like pick place, and then we can start picking. Choose a control interface, joint positions, all these things are there. Okay, and this is very normal that the control frequency is in the range of 20 to 50 hertz. Then we can already have talked about this observation design. Okay, and mathematically I have talked about this. Now how we can collect demonstration as episodes. So data collection methods are teleoperation. I'm going to talk about teleoperation. For teleoperation, we can use joysticks, we can use VR headsets, and in almost all colleges these VR headsets are available. So we can think about using our Oculus headset for teleoperation of this physical kinesthetic. All these things are very regular things. Then episode robot, reset robot and environment, record full trajectories. Again, I have talked about it. Log data at every time step, observation, actions, and time steps. What are the include both successful and imperfect demonstration. Imperfection is required. If your robot is failing while data collection, it's good because our model becomes then robust. Vary object poses, speeds, and scenes. So this is about data collection. And here now I will, for next 2 to 3 slides, I will talk about how we can do teleoperation using VR. VR is virtual reality. Using virtual reality data set, virtual reality headset, like see, I can show you here. So this video you can see. I hope my video is available. So what this girl is doing? So this girl is. So you can think this robot as a, so this as a follower robot. Again I will show. So what this girl is doing? She is operating this robot using VR headset. Okay, and that model of the robot is available in tools like, or the softwares like, or frameworks like Unity, or you must have heard about Unity. No? Unity is there. Okay, so you can use Unity, Oculus headset, or for that matter any headset, and you can connect your robot. You connect your follower. So this is follower robot. Ideally there can be a leader robot and follower robot. So here the function of leader is achieved by VR headset. Okay, so now I will talk about this, how we can do this, and this is doable. So I am explaining over here. We can also do that. User teleoperates a physical robot using a VR headset, and you just go to this this thing. So you go to this. Everything is given over here. Okay, we can just see various examples are given here, and how we can use those examples for teleportation or teleoperation. Okay, so everything is given over here. So Unity is game engine, and this is freely available. Anybody can install Unity, and for that matter, Oculus headset, Quest 2 or 3, it must be available in your college. So you can use Unity or Oculus Quest 2 or 3 for this teleoperation. And if you don't have follower robot, you can integrate this your Unity Oculus with Mujoko. Mujoko is a physics engine, and through simulation you can generate the data, because very beautiful environments can be created using Unity and Mujoko. So if you really want to experiment on it, even this follow robot, that is hardware robot, is not required. Real robot is also not required. So you can only work with simulation. Not only that, D robot runs AI assisted control and safety logic. All these things are there. So we can collect what we can collect. We can collect vision. We can collect even language, and we can collect all this pre-proprioception data by using Unity, Oculus Quest. Real robot is there. Okay. Otherwise, you can use Mujoko or any physics engine you can use. And how you do this? So how this thing is happening? User moves head, hands, and controllers. VR headset and controllers track pose and gestures. Unity, that is Unity game engine, captures real-time VR input data. VR input mapped to the robot commands. End effector pose or joint targets are computed. Inputs are normalized and time stamped. And how these observations, packaging, and communication is done? Unity builds observation packet, include target pose, control mode, and context. Data is serialized for network transmission. Observations sent to Python service. Either you can use WebSocket if you want low latency. If you want, you don't want to waste your time like 20 hertz, or you want um, 10 hertz uh, latency, you can use WebSocket. Or if your application is REST based, then you can use REST used for low frequency command. So you can use web, or you can also use REST API for the communication between Unity and Lay robot, or your server on which Lay robot is installed. And after that, so you can do validation of the data, store, validate, and reuse the data set. So this is the Lay robot data set structure. Episode based storage. Field includes observation, image states, actions, episode boundaries, quality control. We can check the quality of your data on this. Okay, so quality control is also there. And when I'm saying quality control, you just run the Python codes or Python scripts given by Hugging Face or Lee robot and check whether your data is consistent or not. Okay, so data part is over, and now I'll talk about the training of the policies. What is a policy? A policy is a learned controller that maps observations to actions. So I talk about it again. I'll talk, and this is parameterized policy. So it's a sort of neural network, it's a deep neural network, or it can be a transformer for which we are trying to find out theta by training the policy, and it maps observations to actions. Actions are corresponding to join commands. Executes in closed loop, respecting real world dynamics and safety constraints. What are major policies? Major policy classes in Lee robot are behavioral cloning, supervised learning from demonstration, simple, stable, and data efficient. Another framework or another major policy is ACT, action chunking transformer, transformer based policy predicting temporarily extended action sequence for long horizon tasks. So this is transformation based. HIL, SARL, if you are aware with reinforcement learning, that is not our regular reinforcement learning, that is human in loop. So if anything is happening, we can stop the simulation and we can guide your robot in the simulation, or not only simulation, you can guide your real robot and then take the data while doing this HIL, SARL. This is human in loop reinforcement learning enabling safe and collective policy refinement. So this is one group of policy. This is another group of policy, and these three are very popular: ACT, HISCRL, and Vision Language Action. And this is Vision Language Action. So you can see here convolution neural network or vision transformer, large language model. They are combined together, and they are outputting the action. Actions are nothing but join commands. And multimodal policies, like for example, here we can ask our robot or humanoid robot, please go from one position to another position. Please bring apple from that room to this room. So these sort of things can be done using a combination of vision and language action. And a lot of generalization is possible. Now we'll talk about this. What are these action chunking transformer? So what is this ACT? ACT is a transformer based imitation learning policy. And by this time, most of us must know what is the transformer architecture. Okay, because all these large language models, vision transformers, even audio models, they are based on transformer. And very famous line is there: all you need is attention. Okay, so ACT is a transformer based imitation learning policy. It predicts chunk of future actions instead of a single action. For example, here, it is not a single action. It predicts chunk of action. That means 10 or 20 actions it will predict. Designed for long horizon context with manipulations. And what is the training pipeline? This training pipeline takes input. What are the inputs? Visual observation. Visual observation consists of RGB, image data, depth data, proprioceptive states means what? Joint velocity, joint position data. And what it outputs? It outputs action chunk from AT to AT plus K. For example, T can go from 1 to 50. So it will chunk or it will output next 50 actions. And it will sample one of the action from these 50 actions. And this is the loss function. That means this act transformer is trained by minimizing this loss function. Those who are good in machine learning, they can understand the loss function is optimized, and then you can find out parameter theta. And now this is the act architecture. Okay, so this is now here transformer encoder. Okay, so it takes input as so join commands, then action sequence, position embedding is there, and it will give us a Z style variable, which consists of which combined together, or those who are good in generative AI, they can understand this Z is nothing but a latent variable. So by taking joints and action sequence and position embedding, it will output. So this actually this everything is trained. Everything is trained after training. So this is a supervised learning problem, by the way. This is supervised learning problem. After learning, so it will give you Z variable, Z style variable, which is a latent variable. Now here we can see these are the images. And these images are captured by mounting cameras at various places. And these are what? These are convolution neural network, regular convolution neural network. This regular convolution neural network, what they will do? They will extract the feature. They extract the features from these images. These features are going as input to the encoder transformer. See, this transformer and this transformer, they are different. Okay. Then it is taking joints. This transformer encoder, after training of this, so after training of this encoder, it is thrown, it is discarded. Now Zs are available. So for prediction, it is not used. It is only used at the time of training. If Z is available, so you are inputting Z over here. Now this is going. Now this is encoder. Encoder is encoding all the information. Image, joint position, joint velocities, and the interrelationship between joint position, velocities, and action sequences. Everything is encoded in this Z style variable, which further encodes output of this transformer encoder. Now it is trained. After training of this, what this transformer decoder will do? This transformer encoder, you input over here the images or current observations. You provide here current observation, current joint states, and then it will output the action sequences. Okay, are you understanding? Those who are good in machine learning, they can understand it. Okay, na? So this is, and if you really want to understand, you can just visit this website. So this is the basic paper which is published in 2024, and this is very nice paper. So you can read much about this architecture from this paper. Okay, so this is ACT architecture. Another architecture is human in the loop, SCRL. So what it does, it's a combination of imitation learning and reinforcement learning. So and you can understand that this imitation learning and reinforcement learning like this. For example, if you want our child to walk, or for that purpose, if you want our child or our kid to learn talking, so we talk with him, we imitate the words. When we are imitating the word, the child or the kid, he or she will start talking, and when he or she make mistake, then we correct the mistake. Or sometimes when they are talking very nicely, then we give them rewards. So this reward concept is combined with reinforcement learning. And we are talking, and after our when we are talking, our kids repeating. So that is imitation learning. So everything is combined in HIL, SARL, human in loop, sample efficient reinforcement learning. So what human does over here, and everything is happening on the real robot. It is, by the way, it is not simulation. It is happening on the real robot. We ask a real robot to walk on the ground, and when it falls, we correct the falling of the robot by intervention. So human provides interventions and correctness during the training, not after the training. Designed for safe real world learning. What is the training pipeline? Initialize policy from demonstration, deploy policy on robot, human intervenes on failure, interventions added to the data set, policy refined via reinforcement learning. And when reinforcement learning is there, of course, rewards are there. Okay, and this is how this policy is updated. And this K plus indicates that the policy at K time step is available, and now we want policy at K plus 1 time step. How we can get this K plus 1 time step policy? By going through this training pipeline. And this is what now we have update. Update is a function. It takes current policy, demonstration, that means imitation, and human intervention. And this is addition of this demonstration and human intervention. Okay, so this is how this HIL SRL policy works. And so this is the schematic diagram or HIL architecture. Here also, see, image data is there, control is there, everything is combined together, and finally it is outputting the actions. And basically it is a sort of, if you talk about neural network, the basic architecture is actor and critic architecture. Those who have done reinforcement learning, they can understand it is a actor critic deep neural network. Two neural networks are there. One gives the output, another try to correct the output. Okay, so this is basically a actor critic reinforcement learning deep neural network, which is combined with this vision data, pre-proioceptive data. Okay, and see here you can see this is pre-trained ResNet model. ResNet is a very popular vision model, and here MLP is there. So our regular classifiers, which you do using scikit-learn, they are also available. The encoder is there. So probably this encoder is transformer. So this is image data, and this is position and velocity data. So this is network architecture, and this network architecture is actually this actor and critic architecture. Okay, so this is about HIL SARL. And the final thing is VLA, visual language action model. What is done over here? Policies condition on vision plus language plus state. And this language is these language models are available. So you can take CNN, our regular CNN you can take, or you can take a vision transformer. You can combine with your language transformer like ChatGPT model, and we can input it the joint positions and joint velocities and all other signals, and you can train your this vision language action model. Okay, it enables instruction following robotic behavior. For example, you ask your robot in plain English, pick up the apple, pick up the red ball. So your robot will follow that action by looking at the your Apple or whatever device is there through cameras, and it generalizes across various tasks without retraining. And what is this pipeline? Again, image data is there, language instructions are there, robot states are there, and what it outputs? It outputs action or action chain. Again, it takes, now this is a policy, parameters with theta, it takes image, it takes language, and it takes Q of T. Q of T is means what? Robot state. And it will output AT. And this, it is not a single action, it is a chunk, real-time chunk. So it will chunk 50 or odd actions. And this is the learning objective. Again, learning objective is one, and it is very much common among these. So this is the action, and it's a sort of a supervised learning problem. So you know it, you know this label pi of theta. This is output of this neural network, and you try to find out theta, the expected value of. Okay, so this square loss. Okay, so this is about vision language model, and this is a very big vision language architecture. Again, everywhere you can see CNN or this image data is inevitable, because we also, when we are walking, when we are doing the activities, we look at the things. So vision is very important. So vision is taken. So general robot data, all this data, it is going to this. Again, I already discussed about it. What is this? So this is a combination of CNN, then language model like transformer, or it can be vision transformer, it can be language transformer, and it can be another actor critic network combined together, and which is outputting the policy. Okay, so this is about vision language action model. The final thing is how we can do the inference. Inference means what? Now you have trained your model, you have taken the data, you have taken the real data from the real robot, you have created the data set, you have trained your policy by using these architectures, any of this architecture, and now this policy is available. Policy is available is what? The weights of the neural networks are available. And now you want to run your robot, real robot, on the ground using this policy. So this is inference with real-time chunking. So large flow matching robotic policies like pi 0, and these are very popular policies, pi 0, pi 0.5, small BLA, predict chunks of future actions. For example, 50 steps. It will not output only one action. Chunk inference latency exceeds real-time execution. Naive chunks, so all these things are there. So you can just think that, okay, 50 actions are there. I will sample appropriate action from these 50 odd actions. And it will happen very fast. And it will happen at real time. So because of that, it is called as real-time chunking. So what happens when real-time chunking is happening? Again, you can see over here. Again, this real-time chunking is happening through optimization of this loss function or minimization of this loss function. So any new action, and this is executed action, previously executed action. The loss between this and this over the time period, its summation, this summation with some soft transition mask, they are minimized. So this is also a sort of neural network. Okay, so 50 odd actions are there. You just send those 50 odd actions through a neural network, and then this neural network will give you, by solving this optimization problem, will give you a action, appropriate action, by giving this m of t. Again, we'll decide about this m of t. That is, again, this is the thing to be done in detail. What is this m of t? How we can increase, how we can decrease the latency? All these things are it lies in the details. Okay. What are the research frontiers after all doing all these things? What is still remaining to be done? Long horizon tasks, multi-robot learning. For example, robot swarms are there, or robot soldiers are there, and they are coordinating with each other, and then they are doing something. Then continuous learning. The policy is there. It is like a sort of online learning. A policy is there on the robot. Robot is taking the data, and it's relearning the policy and updating the policy. So this is continual learning, and it happens in our case. Human beings are continuously learning. Then generalization into the new task. So then sample efficiency, physical reasoning guarantee, general purpose robots, foundation models plus embodiment, then learning at a planetary scale. At a very high scale, learning should happen. So these are the research frontiers in the physical AI. And finally, conclusion, physical intelligence emerges from interaction. Lee robot enables data-driven robotics. Learning complements classical control. See, we cannot forget classical controller. See, it is very difficult to throw away PID controllers. Ultimately, PID controllers will drive your motors. ठीक है ना? So this learning is there. Everything is good. म्हणजे सगळं चांगलं आहे. But we cannot forget our PID. We cannot forget our microcontroller. We cannot forget our electric motor. And that's the beauty. That's the beauty of mechanical engineering. Whatever is there, laws are satisfied. Lagrange equation is there, and moment equation is there. PID law is there, or control laws are there, or state space equation is there. We cannot forget that. But this learning complements, and this learning complicates in a very major way to the classical control. Lee robot as a bridge between ML and robotics. Practical pathway to embodied intelligence. And this is open ecosystem for research and deployment. Okay, so this is open. Anybody right now you can start your work. Right now you can start your research in physical intelligence or embodied AI. Nothing is stopping you from taking this research. Okay, so with this, I'll stop my presentation. Thank you.
Hello. Participant can ask the question now. Hello.
Participants, you are welcome to ask the questions. Or if you don't have any question, later you can contact me. We can collaborate and start working
No.
on it.
Just now, I have allowed access to all the participants. Please, you can ask the question.
Sir, good evening, sir.
Good evening.
Good evening.
Hello,
Good evening, sir.
sir.
Unmute,
You have explained about layer robot now, sir. Can you use that application for turtle bots also, like developed by Rig Beta Labs?
Mhm.
Hello.
Pardon, I'm not getting this. You're talking that I have developed this sort of kind in my
No,
lab.
no, 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 no. I am talking about can we use for that to simulate the environments using turtle bot also model, like
Yes,
you have
yes, yes, yes.
showcased the.
Yes, yes, we can do this. So what you can do, see, if you don't want to directly work on real robot, you can take
Okay.
your this turtle, but this thing, and you can simulate
Hmm.
it in Mujoko. Mujoko is also another very good physics engine. It will
Okay.
do literally everything.
Okay.
Okay, so you can try it in Mujoko, and then
Okay.
even you can try it. You can integrate it with the ROS also. It is very
ROS
easy to.
we are doing, sir, because I am a program coordinator for robotics and automation at our university. So we make students to work it on ROS platform.
Yes, yes, you can integrate ROS with Lee robot, because ultimately, see, ROS is very old, and also it is very
Yeah.
mature. So if you want
Yes.
to if you want hardware interface, and if you
Okay.
want this latency between hardware and this simulation or this programming or a controller to be uh, microsecond, then you have to go
Okay.
for real time programming.
Okay.
In that case, you can use micro-ROS for communication between controller and all these policies. And in
Okay.
that case, this ROS, and this Lee robot policies, you can work, you can run this policy on your computer. Your micro-ROS will be there on microcontroller, and the
Mm.
ROS will be there on your computer. So policy, ROS, they will be residing on your server or computer. Micro-ROS
Yeah.
residing on your microcontroller, and the communication is happening through micro-ROS. And that's very
Sir, you have
beautiful. So
shown.
latency also will be very less.
Yeah. You have shown the unitary model humanoid robot. We have unitary model quadruped robot.
No, yes, yes. What is this? Quadrupedal is there.
Yes, yes. Unitary make quadruped.
Very good, very good. Sir, you are from which college?
We are from Vignan University, sir. It's in Andhra Pradesh.
Yes, sir, we can collaborate, because see, if you have this Unitary, then ROS
Mm.
frameworks are available, or ROS interfaces are available for Unitary.
Yeah, we are utilizing ROS interfaces only.
Mhm.
Uh,
So you
okay,
can
sir.
try this.
I will.
See, what you can do, if the
Mm.
cameras are available, you can mount the
Mm.
cameras and you try to generate first data sets.
Okay.
You use those data sets for training any of this policy like ACT, VLA, or HIR,
Okay.
SARL, and you run this
Okay.
policy on your quadrupedal. If it is successful, then you are in the game.
Okay.
Hmm?
I will definitely contact you, sir, if I
Yes,
have
yes,
any
yes,
doubts.
surely, because see, we have very small dog robot. Professor
Yeah.
Kolarkar is there. He's from our
Okay.
college. It's very toy type of thing. And you are having unitary quadrupedal is very good. That means you have a lot of potential, sir.
Yeah.
Have you integrated ROS with quadrupedal?
Yeah. We have integrated already. We
Then it
have
is time
acquired.
for Lee robot, because see, Lee
Uh,
robot is at slightly higher level. Physical, we are talking about
okay.
embodied AI, and I think we
Okay.
should enter into that.
Okay.
Mm.
I will contact you, sir,
Yes,
for the
yes, surely,
workshop.
surely.
We are
I will be
planning
happy
a
to
workshop
collaborate.
also in the mobile robotics for
Yes,
FDP. So with our models, so we will. I will talk to you.
yes, yes, surely, surely.
Thank you.
Any more question? Yes, participant can ask question. Okay.
No
You have any
question,
question? You
sir.
can. Okay. Okay. Uh, Actually, see, Dr. Vatir sir completed their PhD from IIT Bombay in mechanical engineering, but recently sir have completed one bachelor course, BS in data science from IIT Madras. So in this age, sir is learning and trying to uh, make machines integrated with AIML tools. So I sincerely thank Dr. Vatusave for delivering an excellent session on robotics, highlighting the crucial role of mathematics in robotics and the use of advanced optimization tool. The session was highly insightful and it was an enriching experience. I also thank all participants for their patient listening. And once again, I thanks, sir.
Okay, I also thank Dr. Rita Pure, who is a very good friend of mine, for providing me this opportunity to talk on this very recent topic. And again, 180 odd participants are there, and I will again appeal to all of you. Please contribute into the area of physical AI, because this is ours. This is mechanical engineers domain, and we should enter into that. Okay, so with this, I again thank organizers for providing me this opportunity. Thank you all
Yes, yes,
participants,
yes.
and all the best.
Thank you, sir. Thank you, sir.
Thank you, sir.
So we have yes, we have a second guest for second session.
Ditapure sir, shall I leave the
Bo-
meeting?
yes, sir. Yes. Thank you, sir.
Okay, thank you.
Sir,
Borode, sir.
sir, feedback link is
Yes, sir.
asking for
Yes, sir.
this thing, sir, access. How to submit it?
Link is asking access.
Yeah.
Okay. I will provide modified link in WhatsApp group. Yes, sir.
Yeah.
Sir, one thing is there. Really excellent session was there. Just can you ask speaker to share his PPT if
Yes,
he
sir.
don't have?
Yes, sir, I will share
PP
it. So I will send it to Dr. Ditapure sir. So don't worry
Yeah,
about
sir.
it.
Thank you very much, sir.
PPT as well as the recording will be shared.
Presentation. How many?
So, Ritapure sir, can we start with our second session?
Feedback link require access. Kindly provide it, sir.